So now that we talked about sort of why would you want to use concurrency and parallelism, let's talk about the benefits that accrue from this. And this really kind of zeroes in on those quality attributes that we talked about. So we'll start by talking about performance. What's the performance? So using concurrency and or parallelism, I'm kind of using those terms interchangeably here. How do we get things to work? Well, first of all, what does it mean? What does performance even mean, right? What does the term mean? So it's basically, there are various definitions. You can read about them here at this link. They have to do with characterizing the amount of useful work that can be accomplished per unit time. And one thing to do is you can decrease the response time required to handle requests. So if it used to take, 3 seconds to do a web search, and now it takes 1.5 seconds or 1 second, you've decreased the amount of time for handling the same request. So that's one way of improving performance. So it's about doing, the same work in less time, kind of along the lines of what we were just talking about the price, right? You get double the quantity for the same price. And there's various ways of looking at this, right? So this concept of response time has some dimensions to it that are worth unpacking a little bit. So one dimension is service time. How long does it take to do the requested work? So if the service you're trying to do is, a web search, then part of the amount of thing there is how long will it actually do to find matches for the search phrase or the search words that you typed into your browser. So that's sort of the service time. Another dimension is wait time. How long does it take for the request to sit in a queue before it gets to run, right? So that's actually different from service time. So there's a lot of things in life where the actual service doesn't take very long, but waiting in line to get service takes a while. So if you go to the drive-through, you go to a drive-through restaurant and you just want to order like a soda or a soft drink, the service time may take very little time at all. But if there's 50 people in line waiting to get a soda or waiting to get some other piece of food, you'll wait for a long time. So that really has to do with queuing and how long it takes to wait for service. Yet another dimension which is important in networked systems, not always so much important in a single computer, but when you start networking computers together, the issue is transmission time. How long does it take in order to generate the request in the client, the sender, and ship it over to the server in the cloud somewhere, many hops away in the network, in order for the thing to sit in a queue to wait to be processed, right? So if you think about everyday life, there's all kinds of examples of people trying to optimize different parts of this process, right? So take a look at, for example, like Amazon and service fulfillment. So one of the big issues used to be transmission time. How long did it take to ship something from wherever it was coming from to your home? Well, obviously, companies like Amazon and others have really been working hard on trying to decentralize their fulfillment centers so they're as close as possible to where people are buying stuff. And nowadays, you can often get things shipped, pretty much like overnight or maybe even the same day if you live close enough to a fulfillment center. It's also quite fascinating how often things we do in everyday life to optimize system performance or optimize the performance of human-centric systems have corollaries in the concurrent and parallelism world. And I'll talk about this later when we talk about other topics. My favorite example is fast food restaurants because they use various techniques to increase throughput, and computer systems often do something very similar. Another dimension of performance is increasing the amount of work that can be performed in a given time, which is not unrelated to the first one about decreasing response time. You can imagine those things working together. But this is really about saying, if I've got a minute to do processing, how much work can I pack into that minute? Now, of course, if you can make each work request take less time, you could probably pack more things in. But these are not always identical issues, right? So one is really about latency, the other is more about scalability. And sometimes they're the same, sometimes they're not. So this is really about throughput. And again, I think I mentioned the Spinal Tap movie is a great example of turning up the volume, right? You want to go and make it work at the maximum performance. So decreasing response time and increasing the amount of work performed within a given time are common motivations for using concurrency and parallelism. That's why you want to do this stuff. That's nominally why you want to do this stuff. And it's kind of funny because sometimes people think, oh, well, gosh, if I have multiple cores and I've got a programming infrastructure like Java 8 that supports threading or parallel streams or completable futures or whatever, I'll just be able to kind of magically turn on the parallelize switch and everything runs faster. And it turns out it's not quite that simple, but that's what we'd like it to be. We'd like it to work that way. The reason why it's not quite that simple is there's often trade-offs between performance and productivity. And so historically, the ways that we develop software to make it run fast were often at odds with the way we develop software to make it easier to develop in a timely manner and in a correct manner, which is often even more important than making it timely, although not always. So there's these trade-offs between productivity and performance. Can anybody think of some examples of trade-offs where people have emphasized performance at the expense of productivity? What would be an example of that you could think about? How could you make something run faster but make it harder to maintain or develop or evolve? That's a good observation. Sometimes it takes more to build a tool that automates something, and unless you're going to do that for the next 20 years and save yourself a lot of time, it's not worth it, right? It's also why it's often easier to do the work yourself than to get a group of people to do it for you, right? Because it takes longer to explain it to them. That's an example, although that's not quite the example I was thinking of, although it's not far off. Yeah.
One example that I'm thinking of is PlayStation, the unique really when you could
That's a great example, right? So that probably was sort of, I think they called it the cell architecture. There was a name for it, and they had special purpose CPUs, or sort of almost like GPUs that did very custom things, but you couldn't do general purpose processing, so you had to build your program in a way that decoupled the special purpose stuff from the general purpose stuff. There's actually a name for that these days. It's called heterogeneous parallelism, heterogeneous parallel computing systems that have some CPUs, some GPUs, maybe even some DSPs. And it's becoming actually increasingly popular. In fact, I think we talked about that last semester in the context of, was it big little architectures? But it still is hard to program. So that's a really good example. So anything else you can think of? Yeah. Exactly. That's really what I was thinking about. So if you program everything in assembly code, or C, which is not that much different from assembly code, it's likely to run faster, at least in one sense of running faster. It's likely to have, the computations have as little overhead as possible. On the other hand, it'll take forever to build and forever to debug. Moreover, if you program in assembly code, the kinds of things that you would do to take advantage of multi-core may be almost impossible, because you probably wrote your assembly code program to be single-threaded, because the concept of trying to write a multi-threaded assembly code program is mind-bogglingly complicated. So you can't take transparent advantage of these things. And so there's all these different trade-offs. And the point here is not to say one thing is good or bad. It's to point out that they're trade-offs. So one of the things that you'll need to learn over your careers, and you'll have to keep relearning it over and over again because things keep shifting all the time, are trade-offs between different quality attributes. And performance and productivity are one important one. We can accelerate performance via parallel processing if we do it right. So we can have multiple things running, and we can perform computations simultaneously. So you might have some kind of image processing algorithm, and you want to do gang scheduling, where you're going to schedule the work with a pool of threads or pool of cores, and each thing works on a different part. This works very well for so-called embarrassingly parallel programs. We'll come back to this topic again, although we'll talk less about embarrassingly parallel stuff in this class than we would talk about in a parallel computing class, because the gold standard of any program to run in a parallel computing environment is it embarrassingly parallel? And that's a funny term. Sometimes people say, what the heck does that mean? It means that there are no dependencies between the tasks that are running, so you can have them run on parallel processors and they just go full tilt and never have to worry about synchronizing or coordinating with other threads. The example I always like to use in this case is a laundromat which has a bank of washers or a bank of dryers. And if you have a lot of laundry to do, you can go in there and you can put your laundry in all the washers and you can run them in parallel, and there's no dependencies between the loads, right? You're just running there, and when you're done, you can, if you have 10 washers, you can get your laundry done 10 times faster than if you had one washer, because you can run them all together and you don't have to worry about dependencies other than having to take them out and put them in the dryer. Typically, when we do parallel processing, we use a divide and conquer like approach, where you take a big problem and you break it up into smaller problems and run those things in parallel. We talked a bit about that last time when we talked about the motivation for parallelism. The map-reduce paradigm is a common way to do this. You map your tasks into subtasks that are then processed in parallel, and then you reduce them back to a single result. That's why Google web searches are so fast, because they do map-reduce. They take your query, you're looking up something, and they map it to a gazillion machines out there on the internet, each of which have their own copy of the web or their own copy of a portion of the web. They get their results, and then they merge them all back together again. So that's a map-reduce model. Image rendering is one example. Another example, you could have different threads rendering different parts of a complicated image. That's, again, why things weren't so good in the early days of Star Wars, because they had really crummy computers relative to what they have today, so they can do a lot more work. Android and Java, but we're focusing on Android because that's the platform we're using for the class, enables parallel computing and concurrency by overlapping computation and communication by two frameworks. And the frameworks that are provided in Android are the Hammer framework and the async task framework. And you'll get a chance to play around with both of them by the time we're done. Hammer stands for handlers, messages, and runnables. And that's a very simple framework. And what it does is it allows operations to run in the background threads, right? This is sort of the classic definition of concurrency. You have background threads that run, that do long-running processing, like downloading a file or rendering an image or whatnot. And when they're complete, they post a message or a group of messages to the user interface thread via the user interface thread's message queue. And there are these little abstractions called a handler, and a handler is basically a proxy that allows a background thread to post a message to another thread. And so it uses the message to put into the message queue of the handler, and then the user interface thread will pick out the messages and do something with them, like display them or prompt the user or whatever you want to do. So that's the Hammer framework, and it's basically a message passing framework. If you recall, in the last class I talked about people who want to write applications often want to use these higher level frameworks that use message passing because they're nicely flexible and decoupled. The way this works under the hood is you spawn Java threads, just like you're doing in assignment 1A, and those threads run in the background. They're just good old Java threads, and then they use the Android Hammer framework API to post runnables or send messages to other threads, in this case, typically the user interface thread. The second framework that Android provides, which we'll also get a chance to play with and you get a chance to program, is called the async task framework. And this is a much more interesting framework in many ways. It implements a richer set of patterns. It implements some patterns like the template method pattern, hopefully you've learned about in CS 251. I'll remind you about it later when we get to that point. It also implements another concurrency pattern called the half sync, half async pattern. And this model provides an object called an async task, and this object allows one or more, it allows operations to run in one or more threads. You can actually have a pool of threads in an async task environment. And they run in the background, and then they publish their results back to the user interface thread via various callbacks. These are hook methods in the template method pattern sense. And you give work to an async task by telling it to execute. So that's like the template method in the template method pattern. And then it has a bunch of hooks on pre-execute, on progress update, on post-execute, and so on. And these hooks get called back in the appropriate context at the appropriate time. There's a do in background that runs things in the background. And these things run and do the work and then interact with the user interface thread. And one of the cool things about this framework in comparison to the Hammer framework, where you have to explicitly allocate threads, you have to explicitly send messages or post runnables, you have to deal with handlers, you have to do a fewer lower level things. With the async task framework, you can have a concurrent program without having to really know anything about threading, handlers, messages, runnables, and so on. You just make an object, you say execute, and it goes ahead and runs the processing in the background and then gives the results back to the user interface thread through method calls. So it's nice and clean and easy to understand and much more pattern-oriented, much higher level. So you'll get a chance to play around with that. Under the hood, the async task framework uses something called the Java executor framework to run the tasks that you give to async tasks in a pool of threads. So this is cool because it illustrates a whole bunch of other patterns like resource pool and so on. And so we'll talk about this stuff and you'll get a chance to learn about that. And the second programming assignment you'll do in the class here will re-implement the Palantir manager, or the Palantir simulator, using a thread pool model using the executor service. So we'll talk about that later too. Okay, so that's a quick overview of some of the performance benefits from using concurrency and parallelism in Java and Android. And the basic issue here is make things run in parallel or make them run in a way where they can leverage the available cores. So the next topic here has to do with responsiveness. And the key goal is to avoid either the spinner icon or the hourglass icon. This was kind of the one on the right for your view. The hourglass is kind of the way the Mac used to demonstrate this. The one on the left is kind of the way that Windows would do this. You very rarely see these spinners anymore for the reasons we're about to talk about. So what are some of the impediments to leveraging hardware parallelism? Right? So I just got done telling you about all this great parallelism stuff. But even though it's potentially available, there's sometimes reasons why we can't make things run in parallel, even if we'd like to. So one reason, although an increasingly irrelevant reason, but still around if you program in legacy systems, is that not all computing platforms support all this great hardware stuff, right? Some things are still running the older, Model T equivalents of the hardware. So you've got lots of computers, if you happen to be programming a Mac SE or a early version of a Android device or a Nokia device or whatever, you're probably not going to have multi-core processing, and so you're not going to take advantage of all the things we just talked about. It's also sometimes hard, even on platforms with multiple cores, right? So like my cell phone has 4 cores on it. It's sometimes hard to leverage parallelism due to various impediments in the software and other things that are just more fundamental to parallel computing. So one reason why you might not be able to leverage parallelism is you've got code on your system that's legacy code that's not thread safe. So when people developed it, it was not designed to be used in a multi-threaded environment. So as a result, it's not thread safe. So as a general rule of thumb, for example, if you have programs that access global variables or globally visible objects, and those globally visible objects are not protected by locks, then you're going to end up with race conditions, which, as we've talked about before, are these tragic concurrency hazards that occur when multiple threads smash into some shared mutable object state and they corrupt it by changing it simultaneously and getting weird results. So a lot of legacy code was written way before we had multi-threading, and even some poorly written modern code that uses a lot of global variables is not written well, and so you'll have these kinds of problems. Another reason that's perhaps more design-centric, but no less pernicious, is the fact that GUI frameworks, GUI toolkits, graphical user interface toolkits like Android and others, JavaFX and so on, and the iOS, are not designed to be thread safe. Intentionally, they don't make them thread safe by design. And there's a couple of reasons why that's the case. Number one, they didn't want to have to put locks in the user interface code because it would potentially slow things down. So they just kept locking out of all the code that updates to the display, things like dialogues and menus and widgets and all that good stuff. And the other reason why they didn't do it is they didn't want to have everybody and their dog who was an application developer need to become an expert at concurrent and parallel programming, which, as you'll discover as you get more into it, is sometimes tricky because of inherent and accidental complexities. So they intentionally made it the case that you do not have the ability to have UI code run in multiple threads. And so as a consequence, Android only allows the user interface thread to access the GUI components. And if you read about it at this link, it'll explain why. So there's only one thread, right? This thread here, the one that's the thread that's interacting with the user, gets to do stuff in a single thread, and other threads that are doing work have to run in a background thread. Yet another reason why we can't always leverage parallelism is because of something called Amdahl's law. And basically, Amdahl's law says, it's a very fancy mathematical equation if you read it, but basically its point is that the ability to speed up a program on multiple processors or multiple cores is a function or is limited by the amount of sequential code that cannot run in parallel. So in almost every program, there's some code that you can break up and run in parallel, and there's other code that sort of fundamentally has to be run sequentially. And if you have a lot of that kind of code, then it doesn't really do you a whole lot of good in a given program to have multiple cores because you can only do one thing at a time. So, of course, the goal there is to improve your parallel algorithms, but not everything lends itself to that. So how then can we use concurrency to improve responsiveness if we're in these situations? Well, we can use concurrency to improve perceived response time. So it's kind of like, sleight of hand or a magic act. So one way to do that is to not ignore user input while long duration computations or communication are occurring. I'll give you a very simple example. I think, yeah, here we go. So you go to an ATM machine and you swipe your card, and then there's a menu and you get options and you put your PIN in and you select which account you want to do or what operation you want to do and so on and so forth. And of course, chances are, of course, these days this may not be different. This may be different, but back in the day, the ATM was not a multi-core processor. It was probably a very simple processor that was just doing the minimum things. And so what they're doing is, they're walking you through a bunch of menu items while they're out validating that your card is, your card is valid and that the PIN matches the card, and they're finding out your balance on your account and all this other good stuff. And so all those things are taking place sort of in the background, and they're kind of walking you through a bunch of menu items. And the whole goal there was to be able to minimize latency by hiding the fact that stuff was taking place in the background. So the UI is responsive, but there's still things taking place that are going on in the background. And you could do that with a single core machine quite nicely by having a multi-threaded solution. So the idea is that, don't slow the user, or don't slow the user down. The user may be slowed down, but give the user the appearance that things are making progress. Very much the way that when you call up a call center for a Visa card or to do something that requires talking to an operator, like get your modem fixed in your house network, there's like 27 menu items that they walk you through. And that's all just sort of a way to hide the latency of the fact that they don't have enough people in the call center to handle the volume. So as long as the software infrastructure supports so-called preemptive multi-threading, even single-core hardware can appear to be more responsive. And this is just a diagram that illustrates the difference between preemptive multi-threading and non-preemptive multi-threading. So what you do here is, as you can see, each thread gets a little while to run, and then, irrespective of what it's in the middle of doing, the operating system will switch over to another thread. You'll pause the first thread, save its state off someplace, switch to a new one, let it run for a little bit, switch back. And if the switching takes place fast enough, you really can't tell as a user, as an end user. You could tell if you're measuring the performance, but as an end user, you probably think it's just being responsive. In contrast, non-preemptive systems will have the threads run as long as they feel like it, and they only give up control when they decide that they're done. But the problem there is if one thread decides to go off and do a long-running background computation, the user interface thread will sit there and spin, right? They'll have to wait, which is not responsive. It makes the appearance of not being responsive. So Android provides a lot of cool things to improve responsiveness. And the main way it does it is it has features and idioms and patterns and so on that help to make things appear more responsive. So the way it works is that the UI thread interacts with a user, and that thread, the UI thread, never can block for more than a very short time, a few seconds at most, and they actually enforce that. If you try to block longer than a few seconds, you get the dreaded application not responding error. And then worker threads, as I mentioned before, run in the background, and they can block, right? So we always have a responsive UI thread, and the other threads can take a longer time to run. So that's the way in which Android helps you to avoid these problems where you appear that things are unresponsive. Even if the system actually doesn't run any faster, you have this nice, warm, fuzzy feeling that things are going a bit more smoothly.